Hello everyone, welcome to the tutorial of Chapter 3. In this chapter, we will learn about the basic skills for working with samples from the posterior distribution. In last chapter, we used grid approximation and MCMC to get the posterior distribution. The model's work has done there, but our work just started. Just like in our basic statistics class, after we get the parameters of for example, a regression model, our job just started. We need to make the correct inference from the result, and we also need to do the same thing in Bayesian statistics. We're usually required to answer questions like how much posterior probability lies below some parameter value, or which range of parameters contains 90% of the posterior probability, or which parameter value has the highest posterior probability. Past statistics class, these questions I've mentioned are answered with the help of some math formula. For example, we have formulas to calculate the confidence interval for a regression problem like this one. However, in this class, we use another approach. Since the model gives us the samples from the whole posterior distribution, we can make inference from it. So firstly, let's answer the question, what is a posterior distribution? So the posterior defines the expected frequency that different parameter values will appear. So the posterior distribution from the grid approximation will show the expected probability of each possible p-values. And in this example, the p-values will be the proportion of water on the Earth. The grid approximation generates the whole posterior distribution. We have the density, probability density at each possible value of p, whilst then gives us samples from the posterior. Approximation is better because we have the exact probability density at each p. However, in most cases, we can have the posterior distribution, but only samples. As mentioned in previous tutorial video, grid approximation only works in very simple example. It's a more general approach. So in this chapter, we will begin to use samples to summarize and simulate the model output and make our inference. On our journey to working with samples. So for grid approximation result, it provides us with the exact posterior density. However, we want to make inference using the samples, so we have to draw samples from the posterior first. And here I copy the cost from Chapter 2 tutorial, and it's exactly the same, and we can calculate the posterior distribution and store the information in the data frame D. Or to sample from the result of grid approximation. Firstly, we can set the sample size, and I set the sample size to be 10,000. And then we can use the built-in sample function in R to do the sampling. So the first parameters is the things we want to draw. So it will be the p-values in the p-grid. And the second parameter is the size, how many, this is the stress sample size. And third, it's the probability of each thing we want to sample. So, for example, this will be our posterior. So it means that the probability we draw p equal to 0 is also 0. And the probability to draw sample of 0.04 will be this. Besides, we have to set replace to true because we want the p-values in p-grid can be drawn like more than once. And also I want to record the order of each sample. I mean, I want to know which sample, what is the first sample I draw, the second sample I draw, so I add one column to record the number of samples. Check our result of our sampling process. And firstly, I plot the samples and the sample number on a scatter plot, and you can see that all the samples we draw are from 0 to 1, and you can see that from 0.6 to 0.7, the colors are darker, which means we draw more samples in this region. Also, we can see the density plot from our samples, and you can see that this density plot is very similar to the posterior distribution we calculated using D binomial. And this is also why we can use samples in MCMC to get the inference of a posterior, even though we don't have the exact posterior density function. Here I will teach you a new function called grid range, and this function is in the package of grid extra, and this function can help us put two plots in one big plot. So just need to put the two plots or more than two in the function and set how many rows we want So and we can get a beautiful result by put these two plots together in one plot. And we can check the result of MCMC. And MCMC just gives us all the samples it draws, so we can work directly with its output. See, we can just use the as the data.frame function to get the output of P. And we can draw the same plot as we did in grid approximation, and you can see that the results are very similar, especially you can see the MCMC results and the grid approximation results. The density plots are very similar. So in the following tutorial, I will only use the grid samples data, and the output will be very similar if we change grid samples to MCMC samples. Here are the questions for interval estimation and point estimation. So firstly, we may be asked that how much posterior probability lies below some parameter values. Like for example, what is the probability that proportion of water on the Earth is lower than 50%? So it's actually very simple. We just need to use filter function and get all the results, all the samples that's smaller than 0.5. And then we can use the summarize function to count how many rows are in this data. And then we can divide the count to the whole sample size to get the probability. So from this result, we can see that, okay, we have 1,006, around 700 samples that are smaller than 0.5, and the probability will be around 17%. Also, we may be asked that like how much posterior probability lies between two parameter values. So it's basically the same logic. We just need to change the filter conditions in the filter function. So if we want to know the parameters, the probability between 0.5 and 0.75, we can just set the condition here, sample probability larger than 0.5 and smaller than 0.75, and use the summarize function again. So the result will be, okay, there are 60% of the samples lies between these two parameter values. If we want to get 90% percentile, and the result is 80%, and we can check from the density plot, and 80%, yeah, it contains about 90% of the samples we have. We may also want something like kind of confidence interval, like we want 50% samples on the right and 55% samples on the left. This is called percentile intervals. So if we want a 90% percentile interval, we will get a 5% interval and 95% intervals. And in this region, we will have 90% of the samples. Also, these work. So the function we use here is pi, which represents percentile intervals. And also, actually, this pi 90% percentile interval function is the same as quantile with probability at 5% and 95%. So we can see that these two results are exactly the same. Wondering why the percentile intervals are 5% and 95%. Actually, we can find infinite intervals that contains 90% of our samples, right? So here we need a new concept, HPDI, and it's the highest posterior density interval. Simply speaking, HPDI is a stricter PI, and it must be the narrowest PI. So HPDI must contain the region with the most samples. Also, we may usually want to find a point that can represent the whole posterior, and this is the point estimation. And in Bayesian statistics, if we want to do point estimation, we must define what is our loss function. And a loss function is a rule that tells you the cost associated with using any particular point as the whole estimation. So if we define the cost of any p to the absolute value, to the true value, and the loss function will have the median will be the best point estimation. And if we define the cost to be the quadratic distance, and the mean will be our point estimation. But for some problems, we may need to customize our cost function. For example, in a rainy city, if we want to predict the weather, either median or mean prediction will not be good enough, because in a rainy city, the model just need to predict the city to rain tomorrow, and we will have very great accuracy, but this is not what we want. So this time we have to customize a loss function and give rainy day a smaller cost and give sunny day a higher cost. By doing so, we can get a better and more reasonable estimation or prediction for our problem. Task for us is to perform backtest. So after we get the samples of our parameters, we can generate fake data using these parameters to see if the parameters we get is consistent with the data. We would like to know that how often we can get 6 water from 9 joules when our P follows the posterior distribution. Apply the random binomial function into the samples we have. So we set each probability of random binomial function to the samples here. So this rule means when we set the probability to 0.45 and the random binomial result count is 4 water from 9 joules, and when in this case will be the probability to be 90%, and we get 9 water from 9 joules, and so on. Plot the fake Q we just generated on a histogram to see how easy we can get 6 water from 9 joules. End of this tutorial, I would like to explain this complicated graph on the textbook in details. And for a while, so I really want to share my understanding with you. Produce the graph in R using ggplot. So if you want to know how to have a graph like this using R, and don't forget to check the R markdown file. Let's start from the first row of this graph, and basically this graph is the posterior probability of our parameter P from grid approximation or MCMC. So the x-axis of this plot is the different proportions of water, and the y values are the probability density in the posterior distribution. So for example, the probability when there are 0% of water on Earth is 0, and the probability for like 60% of Earth is covered in water is 0.25. So these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns represents when the proportion of water equal to 0.2, 0.3, 0.4, 0.5, 0.6, 7, 8, 9 to 1. And for the second row of the graph, it's basically the random binomial distribution under 9 joules and with P equal to different value. You can see that when P is very small, few joules in water are a common situation, and as P goes higher, we can see more joules at like 6 joules, 8 joules, or 9 joules. Of this graph, actually it's the result of multiplying the probability density with the count of each random binomial distribution. By doing so, we can get the weighted distributions of different P. And then we can sum all these 10 random binomial distributions together, and then we can get the result like this. And this is the last row in this graph, and the author call it posterior predictive distribution of samples. Hopefully you get better understanding through my explanation, and it's the end of tutorial chapter 3, and see you next time.